Welcome folks, and in today's lesson we're going to talk about something which maybe you may be able to guess, which just from the diagrams which are popping on screen here. So we have a beautiful piece of artwork, Japanese artwork. We have a creature playing a cello. We have something majestical in the sky and something majestical somewhere else. So what we're going to talk about today are the things that bind the images on screen, and that's the subject of waves. So in today's lesson we're going to talk about what a wave is, how we characterize it, what are different points, and so on. So firstly, let's get the definition out of the way. A wave is a disturbance that carries energy from one location to another. So it's a disturbance, and that can happen in different areas. We're just looking at one on screen here, a little GIF that I've got. Think of a ripple effect in the water and so on. And the material that the disturbance travels through is called the medium. So if it were an actual water wave, the medium will be water. The sound that you're hearing my voice on, that goes through many different mediums, but the last one before it hits your ear would be the air, obviously. And that movement of the disturbance is something called propagation. So there are a couple of different types of waves, two main types of waves. One is called longitudinal and one is called transverse, and we're going to elaborate on what those things are later in the video. Longitudinal waves are sometimes called mechanical waves, and for them you need a medium. You need a medium to transfer that energy from one molecule to the other. And transverse waves, an example of a transverse wave is electromagnetic waves. So the light that allows you to see the screen right now would be an example of a transverse wave. The sound that allows you to hear what I'm saying would be an example of a longitudinal wave. And so this begs the question, how astronauts in space where there's no medium and very little air, how do they communicate with each other? Do they actually hear each other? Do they see each other? So maybe that's something to ponder based on what we've talked about. So let's just elaborate on what longitudinal waves are. Well, we said that they're called a pressure wave, and what's on screen is something called a tuning fork. And now there's far more sophisticated things that you can tune instruments with, but this is an old school tuning fork, which would be set to a certain frequency, and it would make a certain sound when the parts of the tuning fork vibrate and a disturbance is initiated. And you will see that there are different areas, some are darker in color than others, and they form this kind of pattern. And the areas that are dark are represented on screen are areas that we call compressions. So in a pressure wave, a compression is an area where the pressure is more, so the more molecules squeezed into that little amount of area of space. And rarefactions, the lighter areas, in our model we've represented them with just less dots, and those dots represent molecules, so they would be areas of low pressure. Now longitudinal waves are used or appear in many different areas. Music, for example, bats used ultrasonic ultrasound waves to navigate, and also at the bottom you'll see there's a GIF of primary waves, earthquake waves. And one of the things you notice about longitudinal waves, hopefully, is that the direction of propagation of the wave is parallel to the particle's motion. So that's a really important thing to remember about longitudinal waves. Transverse waves, on the other hand, look a little bit different. We represent them as sine waves. And an example would be this person with a slinky. As they rotate the slinky, they move the slinky up and down. The slinky will move, and it will create that sine wave pattern. And the displacement, the particles are going up and down, but the propagation of the wave is to the right. So they are perpendicular to each other. So that's an important feature. And if we look at an example, this is a secondary wave. These are the aftershock waves of an earthquake, and they're far more dangerous than a primary wave. and maybe you can understand why looking at the GIF. But for a transverse wave, the direction of propagation is perpendicular to the particle motion. So how do we represent waves? Well, we tend to represent waves using the sinusoidal pattern that we should be using for transverse waves. So sound waves are not transverse wave, but we often show them as such because it's easier to show the different areas. And those compression areas on a sinusoidal graph are those areas at the top, those positive high amplitude areas, and rarefactions are in the negative part of the pressure on the diagram on the bottom. So the different parts of a wave, let's explain that in a little bit more detail. So we have a pattern. Now it is important to say that this wave is just a snapshot. The wave is constantly moving, but if we were to freeze frame the wave, in the blue areas we would look at what are called crests and troughs, and these are positions of maximum displacement, crests being a positive displacement and troughs being maximum negative displacement. And the maximum displacement we call amplitude, regardless of whether it is, a positive or a negative. That maximum amount of displacement is called amplitude. And when we're talking about waves, amplitude is synonymous with energy. It has to do with energy. So the greater energy, the higher the amplitude. If you were to increase the volume right now, you would get a little taste of the sound waves at a higher amplitude or energy. And the dashed line, finally, is the equilibrium position of the wave. So let's focus on some other wave characteristics. The wavelength, you may have heard of this phrase before. Wavelength is the distance between one crest and the next crest, or a trough and the next trough, and that's called a wavelength, and it's represented by lambda. So it would be the distance between A and F in the diagram, or indeed B and G, or indeed D and I, or even C and H. It's where the wave actually repeats it. You get that repeated pattern of the wave. And so that's the distance between them. And that can vary depending on whether it's sound waves or whether it's infrared waves. So different wave types have different wavelengths. And the second wave characteristics we should talk about is not distance, but period. And period is the time it takes for one complete wavelength to pass a single point. Think of somebody swinging on a swing. It would be the time that it takes the swing to, begin its swinging position and then go back to where it started. So that would be the time for that would be called a period. And I've just put the little GIF here because it kind of looks like a clock, albeit moving backwards. And it would be the time for this little circle to get back to one part of the wave. So how long that takes, let's say the upper part of the wave. And that's represented by the symbol T, a large T, not to be confused with time. So period is the time it takes over the number of cycles. Or another way of putting it would be the time for one cycle. And finally, frequency is the number of complete wavelengths that pass a single point in 1 second. And that's called frequency. On our little nifty gifty here, we have a person moving the slinky, and how quickly those peaks and troughs, crests and troughs move to the bottom of the screen. How many of those pass that point per second is what the frequency is. And we can also see on the image on the right, the bottom right, different types of frequency. Frequency is measured in hertz, and as we're increasing the frequency, hopefully you can see that the wavelength is getting smaller. So there's the wavelength and the frequency are inversely connected to each other. So high frequency versus low frequency. Well, high frequency wave will look like the one on the top, and a low frequency wave is on the bottom. And you can see that there's a difference in the period. So for a high frequency wave, high frequency, the period is small. For low frequency, the period is big. And so there's a relationship between frequency and period. And it's a reciprocal relationship. In other words, the frequency is equal to 1 over the period. And if you go back and think about those definitions for frequency and period, hopefully that should make sense why. So if we wanted to look at those differences in frequency, there's many different online tone generators that you can use that are free, that are wonderful. One is called onlinetonegenerator.com. And so I'm just going to finish by playing some frequencies just so you can hear the difference in those. So at 440 Hertz, that's 440 cycles passing a point in 1 second, we would hear something like this. And if we increase to 650, hopefully we're going to hear, so hopefully you can hear that that's a much higher frequency. So that concludes our video about the different characteristics of waves. Hopefully that served as a good introduction, and if you like this video then please give us a wee thumbs up.